Yeah. Okay. Good morning, everyone. Welcome to the last session of the solid state materials, electron device, and integrated circuits. Well, I am the Dr. Jose Sanchez. I'm going to be the chairman of this session. And today we have three interesting talks focusing on the simulation of solar cells using the SCAPS software. The first presentation is provided by Dinesh Kumar Srinivasan, and the title of the presentation is Design and Performance of Beryl Harding Triselenide Thin Disulfide Heterogeneous Solar Cells at SCAPS 1D study. So please, Dinesh Kumar, the floor is yours.
Thank you for Professor. Good morning, one and all present here. I am Dinesh Kumar Srinivasan, doing my doctorate in energy science under the guidance of Dr. Lata Marasamy in the Faculty of Chemistry at the Autonomous University of Kerala. Today, I am glad to present my title of Design and Performance of Barium Hepanium Selenium Thin Sulfide Heterojunction Solar Cells SCAP 20 study. And this is my overview of my presentation. Our world population is highly dependent on non-renewable energy sources, which are highly pollutant to the environment. Now, we are ready to use the renewable sources because it has some advantages like reusable and environmental friendly. And the renewable resources works on solar energy, wind energy, ocean thermal energy, geothermal energy, and biomass or biogas energy. Now we are going to focus on solar energy. The solar energy mainly used in the applications of solar cells. The solar cell convert the solar energy into electricity. And then now we move on to the working of solar cell. This is the solar cell that we are going to fabricate, which consists of FTO, electron transport layer, chalcogenic peroxide absorber, hole transport layer, and metal contact. Here, the light enters through the FTO, and then the light is transmitted to the N-type electron transport layer, and then the N-type layer transmits the light into absorber layer. After absorption, the charge carrier will be created due to electric field. Built-in potential will be created between p-n junction. Therefore, the charge separation happens. The separator holes are collected through AU and the separated electrons are collected through F2O. And this is the working mechanism of solar cell. The solar cell application in gallium arsenide, silicon, cadmium telluride, copper indium gallium selenide, and perovskite material are highly efficient material. But as you see in the bar graph, the solar cell based on gallium arsenide, silicon, cadmium telluride, copper indium gallium selenide nearly took 40 years to achieve the power conversion efficiency about 20%. But within 10 years, the lead-halide perovskite achieved the efficiency about 20%. Therefore, let's discuss how perovskite material improved the efficiency in particular time. The increase in efficiency of perovskite solar cell along with associated timeline is shown in the graph. Organic inorganic hybrid halide based perovskite was first used in photovoltaics as a sensitizer, replacing the dye pigment in dye sensitized solar cell, which reported in 3.8% in 2009. The device employed a liquid electrolyte as whole transport layer. Device employed the Therefore, the gained little attention due to the low efficiency and poor stability. Later, the liquid electrolyte was replaced by the solid-state HTL, that is a spirometer, which related 9% in 2012. Then, by enhancing the deposition technique and the engineering morphology, the efficiency further increased. The efficiency eventually increased to 25.7% in 2012 by improving the composition and surface engineering. Now, we will discuss the solar cell material which are being used in highly efficient solar cell and their problems. In recent years, mainly used materials are CDTE, CEGS and perovskite material. The perovskite materials comes under emerging solar cell, though they have produced efficiency around 25.7% and has an advantages of low cost and high absorption. They have some key problems such as the stability and toxicity, which hinders the further development in solar cell application. And then the current photovoltaic industry is predominantly silicon based with small share contributed by CDTE and CAGS, and these materials have high stability, high efficiency and high absorption. And then the similar material supply issue exists for CDTE and CAGS, as both of these materials contain rare elements, and CDTE cadmium is a toxic material. So, what can be done to overcome all these problems of conventional and emerging solar cell? Discovering new material will be a better solution. But how? On what basis the new materials can be discovered? As an answer for all this question, we have chalcogenate peroxide, which has the structure form of AbX3, where A contains alkaline earth elements such as calcium, barium, strontium, and magnesium, and B has the transition metals such as hafnium, zirconium, titanium, and finally we have chalcogenate elements such as sulfur and selenium, which are more environment friendly as opposed to the lead-based halide perovskite. Among them, our research, we are going to prepare the barium, hafnium, sulfur, selenium, magnesium, hafnium, sulfur, selenium, strontium, hafnium, sulfur, selenium, calcium, hafnium, sulfur, selenium. And this new chalcogenate perovskite material overcome the challenges of lead galide perovskite material due to the advantages and extraordinary properties such as non-toxicity, high stability, earth abundant, and high absorption coefficient, etc. In this study, we have used the SCAPS 1D software for my methodology. The SCAPS 1D is more convenient and free software for solar cell application. And in this study, the initial solar cell architecture was composed of SLG, AZO, IZO, tin sulfide, barium, hafnium, selenium, copper sulfide, nickel as a back metal contact as illustrated in this figure, and the corresponding material and the structural properties are detailed in this table. And uh, and finally we got the base device efficiency of 1% of one VOC of 1 volt and JAC of 23.58 and fill factor of 51.77% and PC of 12.26%. To further improve device efficiency, optimization was carried out focusing on the buffer layer parameter, specifically donor density varied from 10 power 12 to 10 power 20, defect density altered from 10 power 12 to 10 power 20, and thickness varied from 10 nanometer to 115 nanometer. This impact of this variation on device performance was assessed through the simulation using JV curves, capacitance voltage, March-Schottky plots, recombination profiles, and quantum efficiency analysis, offering the comprehensive insights into the behavior and optimization potential of barium, hafnium, selenium based solar cells. And in this slide, we discuss the performance of tin sulfide donor density with barium, hafnium, selenium absorber. Tuning the donor density, the tin sulfide buffer layer is crucial for enhancing solar cell performance. At donor density up to 10 power 14, the VOC, JSC, fill factor, and PCE remains largely unchanged. Beyond this level, all parameters improved significantly. The rise in VOC results from increased quasi-Fermi level splitting, reflecting a large electrochemical potential difference across layers. In barium, hafnium, selenium based solar cells, high donor density enhances this splitting, thereby improving VOC. At the same time, the improvement in JSC within the 10 power 14 at 10 power 18 centimeter, 10 power 18, the range can be attributed to the strengthening of the built-in potential. And the donor density also affects the band structure of the buffer absorber interface, which is key for charge separation. And then when the donor density is less than or equal to the absorber acceptor density, band alignment remains unchanged, causing little performance variation up to 10 power 14 centimeter minus q. The electron barriers at the absorber buffer interface and buffer and IZO interface also stays high. In contrast, when the donor density exceeds the absorber acceptor level, both the conduction band and valence band in the buffer shift upward, lowering the interfacial barrier and aiding the charge transport. And then and then the and then we can move to the capacity. We can simulate the capacitance voltage measurement, further validate these effects. For at low voltage, capacitance stays in the low due to the depletion capacitance, such as from the absorber buffer interface junction. As voltage increase, the depletion region narrows, leading to the accumulation capacitance. The accumulation capacitance is highest at 10 power 12 centimeter cube, and this capacitance accumulation indicating carrier buildup and high recombination consistent with the large barrier. And at 10 power 20, the barrier is reduced, lower accumulation and enabling the efficient charge collection. This voltage at which capacitance rises also shifts higher with donor density, confirming a wider depletion region. And in the Marcharki also shows that the 10 power 12 have the low built-in potential, that is the 0.82 percentage, and the 10 power 20 have the wow, high built-in potential 1.27 volt. So based on these findings, the donor density 10 power 20 centimeter minus 3 is selected as the optimal level for further simulation. And in this slide, we discuss the performance of SNS2 defect density with the barium hafnium selenium absorber. The defect density within the buffer layer is a crucial factor influencing the performance and stability of photovoltaic devices. To investigate this effect, simulation was carried out by varying the defect density from the range of 10 power 12 to 10 power 20. And then the corresponding changes are showed in this figure from the photovoltaic parameters, the VOC, JAC, and fill factor. In this result shows that the device performance remains stable when the defect density is less than 10 power 14. Beyond this threshold, the gradual decline occurs with the PC dropping from 15.61% to 14.41%, indicating a noticeable reduction in energy conversion efficiency. This decline is primarily due to the increased number of recombination center, which top photo-generated carriers, reducing carrier lifetimes and diffusion length. High defect density also weaken the internal electric field at the buffer absorber interface junction, impeding the electron transport toward the front contact and reducing the charge collection efficiency. The optical response evaluated the quantum efficiency measurement. In the quantum efficiency measurement shows that uh, the device with the lower tin sulfide defect density exceeds the higher quantum efficiency, reflecting more effective photon absorption and improved carrier separation. And these results emphasize that controlling defense the SNS2 buffer layer is crucial for enhancing the both electrical and optical performance, ensuring the optical charge transport, reduce recombination, and maximize the efficiency in barium hafnium selenium based thin film solar cells. So, based upon this, based on this finding, the defect density of 10 power 14 centimeter minus 3 in the SNS2 buffer layer was identified as the optimal condition for achieving the efficiency and stable performance in barium hafnium selenium based solar cell. This value was therefore selected for all subsequent simulation studies in this work. And in this slide, we discuss the performance of SNS2 thickness with the barium hafnium selenium absorber. In photovoltaic devices, the buffer layer thickness is crucial for efficient charge carrier transport between the absorber and the front contact. Its thickness directly affects overall device performance. To optimize SNS2 directly affects the directly ma- affects the device performance. To optimize SNS2 thickness, the efficiency was carried the we can explode it from 10 nanometer to 150 nanometer and evaluate the influence of photovoltaic parameter. As the SNS thickness increased from 10 to 150 nanometer, the VOC increased from 1 volt to 1.12 volt. This enhancement arises from better surface coverage and improved interface quality, which suppresses recombination at the buffer absorber junction. Now, the fewer defect states and strong quasi-Fermi level splitting further supports the VOC and VOC increase, and JSC also showed the steady growth rising from 23.83% 83 to 24.39, mainly due to this enhancement in JSC due to the light absorption and improved carrier generation in thicker SNS2 layer. The trend in confirmed by the external quantum efficiency data, and this shows that the strong spectral response in the visible region and which highlight the improved charge generation rates, and the fill factor arise from 58.47 percentage to 64.38 percentage, which with increasing the buffer thickness linked to the reduced series resistance and smoother current flow through the more uniform junction. However, the simulation suggests on SNS2 separation and collection, the simulation suggests that the tin sulfide thickness of 150 approximately 150 nanometer provides the best balance, delivering the high efficiency, strong carrier collection, and favorable optimal and electrical properties. Careful thicknesses optimization is therefore vital for the high performance barium, hafnium, selenium solar cells. And we move on to the conclusion. In this work, the comprehensive simulation studies was conducted to evaluate the performance of barium, hafnium, selenium-based thin film solar cells, with employing the tin sulfide as the buffer layer. The base configurations, the power conversion efficiency of 12.26 percentage was achieved to enhance the device performance. Key parameters of the SNS2 buffer layer, namely the donor density, defect density, and thickness, were systematically optimized, and increasing the donor density beyond accepted density of the absorber layer due to the favorable band alignment, and similarly reducing the defect density within the buffer layer contributed to improve the charge carrier dynamics, and furthermore increasing the buffer layer thickness was found to be the positively influence light absorption and carrier generation, contributing to higher photo current output. As a result of optimization, the final device is achieved the efficiency of 70.06%, and these findings highlight the potential of barium hafnium sulfur as a viable absorber material in the thin film solar cell, and it demonstrates the effectiveness of SNS2 as a non-toxic earth abundant buffer layer, and this result provide the valuable insights for further exploration of chalcogenate peroxide designs of effectively and sustainable photovoltaic devices. And thank you for your attention.
Dinesh Kumar,
Yes, Professor.
so you turn on the camera, please, for answer the questions.
Yes, Professor.
Thanks so much. So now we have time for questions. So please, if anybody have questions. Okay, Professor Yasuhiro.
Hello, I am Yasuhiro Matsumoto from Solid State Electronics Department, the Electrical Engineering Department here in Shimbesta. Thank you for your nice talk, interesting talk. And I am not so familiar with SCAP 1D, so I have one or two questions regarding the performance of the solar cells. So you mentioned different structure. In this case, it's a heterojunction. So you have several interfaces, HTR, ETR, electrical contact, and itself, the heterojunction. So when you are mentioning about the defect density, what you refer, those in the interfaces, and also in the interface is happening a band offset. So you have a big discontinuity. So what the SCAP is considering regarding this?
Professor, thank you for your question. Actually, you asking asking for the defect density, the energy band alignment, right? What is the energy band movement in the defect density? Are you asking about that, Professor?
Yes. Okay, one is a defect density. That is in general way or some specific defect. You mean in an interface or in a material? Which defect you refer in this case?
In this case, the intrinsic defects we can see, Professor. Let me explain, Professor. Um, uh, in this case, Professor, the vacancies of entrance states create the trap states that promotes a non-radioactive recombination, Professor. The sulfur vacancy donate the sorry in the sulfur vacancy donate electrons with the tin vacancy trap hole and the entrance seal introduce the additional mid gap states, Professor. That's only it can the lower and the lower defect densities have the higher efficiency and the high defects can be low efficiency, Professor.
Okay, in that case, the SCAPS is not possible to consider, for example, the band offset. So the different band gap. So there are some defects or deficiency. I don't know how in detail you can identify those kind of defects or interface states.
Okay, Professor. Let me explain, Professor. First of all, and the SCAPS one, we can explain the first of all, the SCAPS 20 SCAPS 20 performance, Professor. The SCAPS 20 is the most reliable software, Professor. In this case, in the defect density, it mostly reliable to the material properties of the experimental work. So in this case, we are more we are not more exactly like that, but we are more closely to using this, Professor, using this software, Professor.
Okay, I understood. Thank you very much.
Thank you so much, Professor.
Okay, I think we don't have time for more questions, so please take the speaker again. I think we are moving for the next speaker. Yes, please. Yes, yeah. Ready? Camila, please, could you share with us your presentation? Oh, no, sorry. FC Navis, please. You share now the.
Yeah, sure, Professor, sure.
Okay, thank you. So now the next presentation is by FC Navis. The title of her presentation is on the living titanium disulfide as a promising salt transporting layer for efficient barium zirconium trisulfide solar cells, SCAPS 1D perspective. So please, FC, you can start.
Good morning to one and all present here. I am glad to present my research work, which is on unveiling titanium sulfide as a promising whole transport layer for efficient barium zirconium sulfur solar cells, SCAPS 20 perspective. So I am doing my doctorate in energy sciences at the Autonomous University of Querétaro, and my project advisor is Dr. Lata Marasamy. Just a minute. Okay, so moving on to the introduction, solar cells are a renewable energy source and they are environmental friendly and they are innovative energy, they are long term and they are infinite energy owing to their abundance in sources. So the ideal properties of light absorber includes this: it should be cost effective and it should have an optimum band gap. It should be a high absorption coefficient and it should be stable both thermally and then it should be photostable. So this is the device structure of a solar cell, which is consisting of a glass substrate, transparent cathode, electron transport layer, light absorber, whole transport layer, and metal anode. So the working principle consists of just 4 steps, which is light absorption, generation of charge carriers, transportation, and collection of charge carriers. So the light gets transmitted to the glass substrate and then towards the transparent cathode and towards the electron transport layer. After that, the light gets absorbed by the light absorber. So after absorption, charge carriers will be generated, and owing to the built-in potential between the p-n junction, the generated charge carriers will start separating, and the electrons will be collected at the transparent cathode and the holes will be collected at the metal anode. Looking into this NREL chart, it reflects the best research efficiency of all the solar cells. Looking into the line graph, we could see that all the traditional solar cells took up to years and years to reach, decades and decades to reach its maximum power conversion efficiency. So interestingly, perovskites, which falls in the category of emerging photovoltaics, achieved its efficiency of about 26.7 percentage within 15 years, which is really impressive and really motivates us to work on these emerging materials. Looking into the antecedents, in 2009, these lead halide perovskites achieved an efficiency of 3.8 percentage, and in a span of 15 years, it has achieved a breathtaking efficiency of about 26.7 percentage. So these boost in efficiency is due to its advantages in raw material cost and its fabrication cost, and also in turn it gives a breathtaking efficiency. However, they face challenges like toxicity, stability issues, and so these two affects the lifetime of these solar cells, hindering its commercialization. So at present, we need materials which are Mm, which are having advantages of all these of lead halide perovskites, and also it should overcome the challenges faced by this material. So here comes chalcogenic perovskites, which are non-toxic, stable, and composed of earth-abundant elements. So looking into the origin of these chalcogenic perovskites, these are of a generic form AbH3, and in which A is composed of alkaline earth metals, B is composed of transition metals, and H is of non-metals. They show dominance in stability, non-toxicity, earth abundance, and then environmental friendly. This bar graph shows the compilation of publication, both experimental and computational, over the years from 2015. This graph reflects scope on these materials with an increase in the number of publication in a span of 10 years. So in this work, we propose barium zirconium sulfur, which is one of the most widely studied chalcogenic perovskite absorber as a potential absorber for newly designed solar cell. So in this work, we have used SCAPS-1D. SCAPS-1D is one-dimensional solar cell simulation program, which is developed at the Department of Electronics and Information System at the University of Ghent in Belgium. So it helps to estimate the solar cell performance and simulate various properties, and it also helps to carry out detailed study of material function of the entire solar cell device. So in this work, we have designed the solar cell, which is shown in Figure 1, comprised of zinc oxide as an electron transport layer, barium zirconium sulfur chalcogenic perovskite absorber, titanium sulfide hole transport layer, and gold as a metal contact. So in this work, we propose metal sulfide hole transport layer, titanium sulfide as a new novel hole transport layer for our barium zirconium sulfur solar cell, and study its influence in this chalcogenic perovskite solar cell. So we have selected this particular metal sulfide HTL because it has efficient hole extraction properties, which minimizes the recombination losses. All these properties favors because of the favorable band alignment with the absorber. So at first, before optimization, we achieved an initial efficiency of about 13.16% for our solar cell. So after that, what we did was we optimized the whole transport layer's thickness from 10 to 100 nanometers, carrier concentration from 10 power 12 to 10 power 20, and defect density from 10 power 12 to 10 power 20. We varied these ranges for these three parameters to optimize the specified range for the HDL. So now let's have a look into the results for the HCl's carrier concentration. We could see that from figure A, there is an increase in the PV parameters with when the carrier concentration has been improved from 10 power 12 to 10 power 20. So this increase in the PV parameters is attributed to the accumulation capacitance, which is shown in figure B. So when the carrier concentration is less, we could see that the accumulation capacitance is very high. So what happens is that because of this higher accumulation capacitance, electrons and holes at the interface requires more energy to cross the barrier and reach its contacts. Therefore, most of the carriers gets recombined. So therefore, there is a minimal performance when the carrier concentration is less. But interestingly, when the carrier concentration increases, the accumulation capacitance has been reduced as shown in figure B. So when the accumulation capacitance is reduced, the charge carriers move easily towards its contacts without any barriers. Therefore, it refrains the recombination. On the other hand, we could see from the built-in potential from the Motsaki plots in figure C, when the carrier concentration is less, the built-in potential is 0.94 volts. Therefore, it struggles to get separated and reach the contacts, the electrons and holes. When the carrier concentration increases, the built-in potential also increases. Therefore, effective separation happens, and then the electrons and holes reaches the contacts easily. Um, Therefore, resulting in an increase in the performance with an increase in the carrier concentration of the HDL. Next, we could see the influence of a HDL's thickness. With an increase in thickness, we could see an increase in all the PV parameters. But we have selected the thickness of 100 nanometers for HDL because after 100 nanometer, the increase in the thickness is very minimal, negligible. So considering the synthesis time, experimental techniques, we have selected a practical thickness of 100 nanometers. And then we did a comparison for lesser thickness and optimized thickness of 100 nanometer. From figure B, we could see that the Nike spot measurements, two semicircles. The semicircle has been widened for the optimal thickness of 100 nanometer, and the semicircle is less for lesser thickness. So this is because when the semicircle is widened, it displays that there is a higher resistance to recombination of charge carriers when the thickness is high. Contrastingly, when the thickness is less, the resistance to recombination is very less. Therefore, most of the charge carriers recombines, declining the performance. On the other hand, we could see that from the quantum efficiency measurements, there is a decline in the absorption after 600 nanometers when the thickness is less. But interestingly, there is a steady spectral response has been observed with 100 nanometer thickness with its absorption in the visible and in the NIR region. Therefore, there is a huge light harvesting with a higher thickness, improving the performance of the solar cells with its increase in the HDL's thickness. And finally, we could see the influence of HDL's defect density. It is visible that with an increase in defects, there is a decline in the overall performance of solar cells. This is because with an increase in defects, there will be more recombination centers available. Therefore, it traps the charge carriers and it reflects higher recombination, which can be seen in figure B. With a higher recombination of 10 power 20, the recombination is very high, but with with a minimal defect of 10 power 14, the recombination is very less. So this is because with the higher defects, there will be more recombination centers, thereby it reduces the overall performance of solar cells. So finally, after careful optimization of the thickness, carrier concentration, and defect density of our HDL, the barium zirconium sulfur solar cell obtained an efficiency of about 9.58%. So conclusions. In this study, we systematically evaluated the impact of novel titanium sulfur whole textile on the performance of emerging barium zirconium sulfur solar cell using SCAPS-20 simulation software. So initially, the solar cell was designed with a novel structure with a zinc oxide whole transport layer and titanium sulfide zinc oxide electron transport layer and titanium sulfide whole transport layer, and demonstrated an initial PC of 13.12%. And thereafter, we optimized the thickness, carrier constant, and defect density of the HCl. So the results revealed that TiS2s reduce the accumulation capacitance at the interface and enhance the built-in potential, resulting in effective collection of charge carriers at higher carrier concentration. In addition, the titanium sulfate also improves the light absorption and increases the resistance to recombination and optimized thickness. So as a result, we successfully achieved an efficiency of 19.5%. So overall, our findings display the potential of titanium sulfide as a efficient whole transport layer for novel charging perovskite solar cell and emphasizes the significance of optimizing the HCl parameters to attain high performance in solar cells. Thus, we believe that these intriguing findings provide valuable guidance for the design and fabrication of efficient photovoltaic devices, enabling enhanced solar energy conversion and future experimental validation is essential to substantiate these theoretical predictions and guide practical implementation. So these are the references. So thank you everyone for your kind attention.
Thank you, Epsi, for the nice presentation. Now we have time for a couple of questions. So please, if anybody. Yes.
Okay, I have a question. I know that SCAPS 1D is a one-dimensional simulation tool for photovoltaic devices. What
Yes,
is the main reason this perspective was chosen over other based on similar programs?
Okay. So there are many softwares like COMSOL and 2D and 3D dimensional program, but SCAPS offers many unique findings. Like it's one of it's a free simulation software, and it uses equations like Poisson's equations to get a reliable results. And also, SCAPS 1D is most widely used software for simulation for solar cells, while compared to other softwares. And because of its reliability, because there are many research studies, there are many literature and published works that have compared both experiments and theoretical works using SCAPS. So in all of those studies, the experimental findings are closely relating to this SCAPS software. So that's the reason for using this SCAPS 1D simulation program. And all those SCAPS studies has been receiving numerous citations, underscoring the reliability of this software and its availability for users.
Okay, thank you.
Thank you very much.
I have another question. Is it
Yes,
feasible to take this research to two-dimensional simulation?
I don't think so, because both the software uses different equations, and the input parameters might get different, because all these parameters has been taken experimental from the literature, from the experimental values. So there might be some difference in using other softwares as softwares.
Okay, thank you so much.
Thank you so much, Professor.
Our question. Well, I have just curiosity. Maybe I lost this information. Do you know the bancap of your perovskite you are using for the simulation? Because in particular, I saw in your results you have a good VOC, a good fill factor, but the efficiency is quite low, and it's more related because you have a quite low current density. So my curiosity is maybe this one is related to the bandgap of the perovskite.
So here, yes, this depends on the band gap, and also here we have optimized only the whole transport layer. If we are optimizing the other layers, the efficiency might increase, but It mostly relies on the band gap of the material. Because of the band gap, there is a favorable band alignment and favorable offsets at the interfaces.
Okay, another question, one curiosity is if you have prepared or any experimental devices to corroborate your results, or is only simulation?
No, I have been doing my experimental collaborations to simulate, to interlink both simulation and experiments. That's my ongoing work.
Okay, so and last question for my part is if you have any suggestion, for example, you have optimized the titanium disulfide, right? So this is your simulation, and then maybe you have any suggestion to the people who's doing experimental work to how to get this layer with this property you suggest, or you don't have any idea? I don't know.
Yeah, sure. So here we have in this work, I have optimized the HTL's thickness, carrier, and defect, as I mentioned before. So from this simulation, we can, because in experiments, optimizing each thickness and optimizing the carrier defects is very difficult for each and every fabrication. So from this simulation, we can get an overall idea like at which thickness there we could get could get a high performance in solar cell. Similarly for carrier and defect also. So in experiments, we can use various techniques like electrodeposition, chemical vapor deposition techniques to get our desired thickness for our HTL. Similarly, for carrier concentration to achieve this desired one, we can do doping to increase doping techniques to increase the carrier to achieve the desired carrier that we have simulated over here. And similarly for defects, this HTL is more prone to sulfur-prone defects. So we can use sulfurization techniques to get the desired defects that we have optimized via simulation software.
Okay, thank you. So please let's
Thank you very much,
let's take the speaker. And finally, we have the last presentation of this session. The speaker is Kavya Tracy. Kavya, could you share with us your presentation, please?
Yes, sure, sir.
And please remember when you answer the questions, could you switch on the camera, please?
Yes, sure.
So the title of her presentation is Boosting Efficiency of Emerging Copper, Cobalt, Tin, Tetrasulfide Solar Cells with Tin Disulfide Buffer using SCAPS 1D simulation. So please, Kavya, you can start. And please share the presentation. Now it's okay.
Can I start?
Yes, please.
Yes. Good morning, one and all. I'm Kavya Tracy Arukidas, doing my doctorate in energy science at the Autonomous University of Karitaro. And my project advisor is Dr. Lata Marasamy. And I'm really glad to present my results on the title, Boosting Efficiency of Emerging Copper, Cobalt, and Sulfur Solar Cells with WS2 buffer using SCAPS 1D simulation. Moving on to the introduction. Today's world population is highly dependent on fossil fuels such as coal, petroleum, etc., which are hazardous to the environment, and moreover, they are becoming extinct. And now we are in a serious need to find some alternative sources of energy. So these renewable sources of energies come into picture. And among these renewable sources of energy, solar energy is of more attention due to the abundance of the source available. In a single year, nearly 3,850 zetajoules of energy reaches the surface of the Earth from the Sun, and the energy absorbed in 1 hour is more than enough to meet the energy requirements of the human for the whole year. So now we understand is that we have abundant amount of energy. The only thing we need is that we have to harness this energy to convert to electricity to meet the human needs. The technology that converts solar energy into electricity is the photovoltaic technology, and we use solar cells for this process. Now, silicon solar cells like CDTs, then CDT, CAGSC are commonly used as semiconductors in solar cells. However, due to the toxicity of cadmium and the presence of rare earth element in CAGSC, scientists are working on other alternative sources, and copper, zinc, tin, sulfur, selenium is one of the alternative semiconductor which has been used in solar cells. It has a castorized structure. Just a minute, I just want to confirm whether the slide is changing.
I'm sorry, we can't hear you.
Yes, is the slide changing?
Yes.
Yes.
Yes, thank you. It has a castorized structure, and it has some advantages like non-toxicity, tunable direct band gap, earth abundance, and high absorption coefficient. But the problem here is that the highest efficiency so far achieved is around 15%, which is very less in the view of commercialization. The problem in this solar cell is that it has some challenges, like it has anti-side effects. Because of the similar ionic size elements, that is between the similar size of copper and zinc, and due to this there is large secondary phase formation, and as a result of this there is a large VOC deficit which reduces its performance. So what can be done to overcome the problem in this material? So the thing is that we can find new semiconductors by replacing this copper or zinc with large ionic mismatch elements. So in this concern, this copper, cobalt, and sulfur semiconductors are emerging due to the large mismatch, ionic size mismatch between zinc and cobalt. Here zinc is replaced with cobalt, but still it is in its emerging stage, and the highest efficiency achieved till now is it's around like 4.83%, and this is the structure in which this efficiency is achieved. The problem here is that even after replacing this cobalt, we have a large VOC deficit. With this, now here it comes from the unsuitable buffer, that is cadmium sulfide is commonly used as a conventional buffer in almost all solar cells, but it has a very affinity of around like electron affinity of around 4.5 electron volt, which is very large when compared to the absorber. Due to this, there is a large cliff at the interface of the absorber and the buffer, which creates unsuitable band alignment, creating large VOC deficit. So what could be the solution? Now we have to find some non-toxic buffer as well as a suitable buffer that can form a good band alignment with the absorber. So in this case, this WS2, that is tungsten disulfide, this transition dichalcogenide, is gaining attention in recent days as in a buffer or electron transport layers in solar cells, and it has already been used in perovskite solar cells due to it has excellent properties like good conductivity, no dangling bonds, because of which it can form a good band alignment with the absorber. But till now, there are no reports of applying this buffer to this copper, cobalt, and sulfur solar cells. So now in this work, we have used SCAP-SUNDI simulation software to study its potential as an alternative buffer to this solar cell. This SCAP-SUNDI simulation software is a reliable software developed by Mark Bergelman to study the properties of solar cells. Using this SCAP-SUNDI simulation software, we can study the properties of each layer, its essential parameters, and we can investigate the functioning of solar cells without material consumption prior to fabrication. In this work, we have designed this copper, cobalt, and sulfur solar cells in this structure using SCAP-SUNDI. Here, we have also designed a solar cell using cadmium sulfide to compare and show the dominance of tungsten disulfide over this cadmium sulfide. We have used these simulation parameters in SCAP-SUNDI. These parameters are taken from the experiment. Moving on to the methodology, first we optimized the buffer layer, that is both cadmium sulfide and tungsten sulfide, and we compared its performance. And then we optimized the absorber in tungsten sulfide solar cells. And this after that, we carried out a comparison study before and after absorber optimization using these characterization techniques to show the importance of absorber parameters. Moving on to the results, on simulating solar cells with both cadmium sulfide and tungsten disulfide, we could see that the tungsten in WS2 we have a higher efficiency of around like 16%, which is 4% higher than cadmium sulfide. So this shows that this WS2 could be a very good alternative to cadmium sulfide. The main reason for its higher efficiency is the energy band alignment, as that can be seen in the slide. We could see a large cliff-like barrier in the CDS and absorber interface, like around 0.72 electron volt, which is very high. It leads to accumulation of charge carriers. But when compared to cadmium sulfide, in the case of WS2, we could see a barrier of around like 0.17 electron volt, which can result in efficient collection of charge carriers at the front contact. So this is the reason we have higher efficiency in WS2, and this also shows that WS2 could be a potential alternative to cadmium sulfide in these solar cells. So in the coming simulations, we have chosen this WS2 solar cells alone for the further optimization. Further, we studied the importance of absorber optimization. First, we varied the defect density of the absorber from 10 power 12 to 20. We could see that as the defect density increases, the efficiency decreases. It almost stays stable at till around like 10 power 15, and after that it decreases. It happens because of the higher recombination for higher defects. And we also optimize the carrier concentration of the absorber. As the carrier concentration increases after like 10 power 15 or 16, the efficiency decreases, which mainly comes from the improper band alignment, because the carrier concentration of the absorber highly influences the band alignment. Due to the upward shift in the absorber, the barrier height at the interface changes. So the higher efficiency could be achieved only at the optimum carrier concentration, like around 10 power 15, 10 power 16 would be a suitable carrier concentration for this absorber. Then moving on to the thickness optimization, we optimize the thickness by increasing the tuning the thickness from 100 to 2000 nanometer. We could see that as the thickness increases, the efficiency increases, but we could see a significant variation still around like 800 to 900 nanometer. After that, it saturates. It could also be visible in QE percentage, where the QE percentage, that is the light absorption, is highly significantly increases up to like around 800 nanometer. After that, it saturates. So considering the material usage we have used and the preparation process, we have chosen like around 900 nanometer for this absorber as an optimized thickness. And after that, we could see before absorber optimization, the efficiency is around like 16.87%. But after the optimization, we could see an incredible increase in the efficiency of around 24.01%. This clearly shows the importance of the absorber optimization, the essential parameters that we need to optimize in order to increase the efficiency of the solar cell. So in order to have a good more insights on the importance of why this efficiency increased on absorber optimization, we studied we extracted different characterization techniques from SCAPS only to study the intrinsic characteristics, what happens inside the solar cells, so that the absorber parameters have influenced the efficiency. First, we took capacitance voltage. From that we took the Mott-Schottky plots, and from the intercepts of the Mott-Schottky plots we obtained the built-in potential. We could see that before the absorber optimization it's around 0.55 volt, but after that it drastically increases to 1.07 volt, which shows that the absorber optimization influences the built-in potential at the interface, due to high built-in potential, the charge carriers can be efficiently transported without recombination. And the another important thing is that we could see that the quantum efficiency also increases after absorber optimization, revealing that the charge carriers, the light absorption, and the whole process of collection of charge carriers has been drastically enhanced. Also, in the Nyquist plot, we could see that the semicircle of the after optimization solar cell is higher when compared to the before optimization solar cell. This larger semicircle shows that this solar cell after optimization has higher recombination resistance than the before optimization solar cells. So overall, we have an idea that this optimization of the absorber is crucial, as it largely influences the built-in potential, the light absorption, the QE%, and the recombination resistance. Overall, the collection efficiency of the solar cells is highly dependent on the absorber parameters. So while fabrication, it is very important to optimize these absorber parameters to the optimal values in order to get the higher efficiency. So moving on to the conclusion. In this work, we investigated the performance of copper to cobalt in sulfur solar cells with WS2 buffer, and we also compared its performance with cadmium sulfide. And first, we found that this WS2 buffer outperformed the CDS with a higher efficiency of around 16.87%, showing its potential as an alternative buffer for this solar cells. And then we optimized the absorber parameters, and after the optimization, an incredible increase in the efficiency of around 8% is achieved. And finally, we performed a comparative analysis to show the using like CV, QE, CF, and JV characterization techniques for the solar cells before and after optimization to show the importance of the absorber optimization. Overall, the present work shows that WS2 is an efficient alternative buffer for copper to cobalt in sulfur solar cells, and the fabrication of the solar cells with the optimal absorber parameters could enhance the efficiency practically. These are the references. Thank you for your kind attention.
Thank you, Kavya, for your nice presentation. So now we have time for a couple of questions. So please, anybody? No? Okay, I have some questions. First is, which parameter have you optimized for the absorber layer?
Yes, I have optimized its thickness, carrier concentration, and its defect density, sir.
Okay, and do you have any idea how to, in the experimental part, how to get this? I don't know, for example, if you change the composition of the absorber layer?
Yes, in the case of thickness, generally this copper to cobalt and sulfur are mostly in the high efficiency solar cells. The electrode deposition techniques has been used. On using like step-by-step electrode deposition techniques, like by adjusting the thickness of each compound like cobalt, tin, and copper, each layer thickness during the step-by-step electrode deposition, we can control the thickness of the absorber, as well as by varying the composition, we can tune the carrier concentration of the absorber. And another technique for tuning the carrier concentration is that we can increase the annealing temperature for tuning the carrier concentration. And in the case of defect density, as they are chalcogenides, there are more sulfur-prone defects. We can increase the sulfurization temperature or sulfurization time to reduce the defects. And we also can use some like passivation layers at the interface to reduce the defects. So
Okay, and
these
maybe-
are the ways.
Okay, thank you. And then the other question is if you keep the optimized values for the tungsten disulfide when you optimize the absorber layer, or do you also change? Because maybe I lost this. Because I saw the thickness, for example, the tungsten disulfide was 2 microns. So I don't know, the highest, not the highest efficiency, but the lowest defect density. So my question is, if you keep these values and then you optimize, or you optimize at the same time both parameters?
Like you're asking, we have why the procedure, like while doing the simulation, we first optimize the thickness, and I'll keep the optimized thickness, and then I'll optimize the carrier concentration.
Okay. Okay. Well, if anybody else have more questions, so please text the speaker. Thank you so much, Kavya.
Thank you, sir. Thank you all.
Now we finished the session, so thank you for coming. And thank you for all the people connected online, also for attending this session. And that's it. That's all. Thank you.
Thank you.